Imagine yourself drifting quietly through space. There is no rush here, no noise, no urgency, only stillness. Around you stretches a vast ocean of darkness, yet this darkness is not empty. It is filled with distant stars, thousands, millions, scattered like tiny lanterns glowing softly across an endless night. Their light is ancient. Some of these small shining points began their journey long before your planet even formed. Their photons have traveled across unimaginable distances, crossing silent cosmic deserts for millions of years, simply to arrive here, now, where you gently float among them. You take a slow breath. If breathing were possible here, it would feel calm and deep. Space has a strange kind of quiet. Not just the absence of sound, but the absence of disturbance. No wind moves. No waves crash. No leaves rustle. Only stillness. And within that stillness, gravity quietly shapes everything. Gravity is the universe's most patient force. It does not shout or flash. It simply pulls softly, steadily, guiding the dance of stars and galaxies over billions of years. Even now, far away from planets or suns, gravity gently influences your path through the cosmos. If you imagine space as an invisible landscape, then gravity is the slope beneath your feet. You cannot see it directly, but you feel the direction it guides you. And tonight, that slope is leading somewhere unusual. Far ahead of you, among the faint glow of distant stars, lies something that does not shine at all. A place where light itself disappears. A black hole. From here, it does not look dramatic. There are no glowing warning signs or swirling storms. In fact, at first, you might miss it entirely. Because a black hole does not shine. It hides. It reveals itself only through its influence, through the quiet way gravity bends the paths of nearby stars, or through the faint glow of matter spiraling around it. But the black hole itself remains dark. Perfectly dark. You slowly drift closer. Not falling. Not rushing. Just gliding gently through the calm sea of space. And as you approach, something curious begins to happen to the light around you. Stars behind the black hole begin to stretch and bend slightly, as if their light is being gently curved around something invisible. Their shapes distort subtly, like reflections on the surface of rippling water. This strange bending is not an illusion. It is gravity shaping the path of light itself. Long ago, a physicist named Albert Einstein realized something extraordinary about gravity. He discovered that gravity is not simply a force pulling objects together. Instead, gravity bends space. To understand this, imagine space as a soft, invisible fabric, smooth and flexible, stretching endlessly in all directions. When something massive rests on this fabric, it creates a dip. A shallow bowl in the surface of space. Planets make small dips. Stars make deeper ones. But black holes create something far more extreme. They pull space downward so intensely that the fabric folds inward, forming a well so deep that even light cannot climb back out. This is why black holes appear dark. Light can enter, but it cannot escape. You continue drifting closer. And though everything still feels calm, the gravity here is beginning to grow stronger. Not violently stronger, just enough that you can sense a subtle change in your path. The gentle slope of space is becoming steeper now, guiding everything inward toward the same hidden center. If you were watching from far away, you might see gas and dust slowly spiraling around the black hole like water circling a drain. These glowing rings of matter are called accretion disks. As the gas falls inward, friction heats it until it glows brilliantly, sometimes brighter than entire galaxies. Yet the black hole at the center remains invisible. It is a darkness surrounded by light. A quiet absence at the heart of a storm. But tonight, the black hole before you is calm. No violent feeding. No blazing disk of gas. Just stillness. And mystery. You float closer. The stars behind it continue to bend in strange arcs. Their light curves around the black hole like paths around a mountain, forming delicate halos and distorted rings. Astronomers call this effect gravitational lensing. It is gravity acting like a cosmic lens, bending light the same way a glass lens bends sunlight. Except here, the lens is not made of glass. It is made of gravity itself. You pause for a moment in your journey. Not because you must, but because something about this place invites quiet reflection. A black hole is often imagined as something destructive. A cosmic monster devouring everything nearby. But in truth, black holes are simply the result of gravity pushed to its most extreme limit. They are natural objects, born from the life cycles of stars. They follow the same laws of physics that shape everything else in the universe. And yet, they challenge those laws in ways scientists are still trying to understand. Somewhere inside the darkness lies a boundary, a place where escape becomes impossible. Even light cannot cross it and return. This invisible border has a name. It is called the event horizon. But from where you float now, you cannot see it yet. There is no glowing line marking its edge. No warning signal announcing its presence. Just the quiet pull of gravity, growing slowly stronger, guiding everything gently inward. You continue drifting closer. Closer to the darkest place in the universe. And as you approach, another thought begins to form, a quieter, deeper question. Because every black hole begins with something that once shined brightly. Long before it became darkness, it was a star. A star that lived, burned, and eventually collapsed under its own gravity. And as you move slowly toward this mysterious object, you begin to wonder about that ancient moment long ago, when the light of a massive star faded, and the first shadow of a black hole was born. A story that begins not in darkness, but in fire. Before the darkness you see now, there was light. A great, brilliant light. Long before this black hole existed, long before gravity folded space into the deep while you were slowly approaching, there lived a star. Not a small, quiet star like the gentle sun that warms your planet, but something far larger, a giant of fire and pressure, blazing with an energy almost impossible to imagine. If you could travel back through time, billions of years into the past, you would see it glowing fiercely against the dark canvas of space. A newborn star. Stars are born from clouds, enormous drifting clouds of gas and dust that float between the galaxies' glowing islands of light. These clouds are mostly made of hydrogen, the simplest element in the universe, the same element that formed not long after the universe itself began. Over time, gravity begins its slow, patient work. Tiny regions within the cloud grow slightly denser than their surroundings. Perhaps a nearby supernova shakes the cloud. Perhaps gravity simply gathers matter bit by bit, like a quiet snowfall accumulating on a silent field. Gradually, a knot forms in the cloud. Gravity pulls gas inward. The knot grows heavier, denser, warmer. And as more material falls inward, the pressure deep in the center begins to rise. Imagine squeezing something in your hands again and again, pressing tighter each moment. The center becomes hotter, brighter, more energetic. Eventually, the temperature becomes so high that something remarkable begins. Hydrogen atoms begin to fuse together. This process is called nuclear fusion. In fusion, the cores of atoms crash together with such force that they merge, forming new elements and releasing enormous energy in the process. Inside the star, hydrogen fuses into helium, and every tiny reaction releases light and heat that spreads outward through the star's enormous body. Suddenly, the young star ignites. A brilliant sphere of glowing plasma appears in space. And now something extraordinary happens. Two powerful forces begin a delicate balance. Gravity is still pulling inward, trying to collapse the star further and further toward its center. But the energy from nuclear fusion pushes outward. It creates pressure and outward force that pushes against gravity's inward pull. Like two hands pressing against each other. When these forces balance perfectly, the star becomes stable. It shines. This balance can last for millions or even billions of years. For a long time, the star simply lives. It glows steadily in the darkness, converting hydrogen into helium in its core. Light streams outward in every direction, traveling across space to warm planets, illuminate dust clouds, and slowly drift across the universe. From a distance, stars may appear calm and gentle. But inside them, unimaginable forces are constantly at work. Temperatures reach millions of degrees. Atoms collide endlessly. Energy flows outward in waves of light and heat. And all the while, gravity waits patiently beneath it all. For smaller stars, like your sun, this balance can continue for billions of years. They burn slowly and steadily, like long-lasting candles glowing quietly in the night. But massive stars live very differently. They burn fast. Their enormous gravity squeezes their cores harder, making fusion reactions happen much more rapidly. Instead of lasting billions of years, these giant stars may live only a few million. Their lives are short, but spectacular. As the star ages, the hydrogen fuel in its core slowly begins to run out. Fusion slows, and the delicate balance between gravity and pressure begins to shift. Gravity grows stronger. The star's core contracts again, becoming hotter and denser. This new heat ignites new types of fusion. Helium begins to fuse into heavier elements, carbon, oxygen, neon, and eventually even iron. Layer after layer of fusion builds inside the star, like nested shells in a glowing cosmic furnace. But this process cannot continue forever. Iron marks a strange boundary in the physics of fusion. Fusing lighter elements releases energy. But fusing iron requires energy instead of producing it. When a star's core becomes mostly iron, the outward pressure from fusion suddenly weakens. And gravity finally wins. What happens next unfolds incredibly fast. The core collapses inward in a fraction of a second. Imagine the entire center of a massive star suddenly falling inward toward itself, collapsing under its own gravity with unstoppable force. Matter is crushed together more tightly than anywhere else in the universe. Protons and electrons slam together to form neutrons. The core shrinks rapidly. The outer layers of the star crash inward behind it. And then, suddenly, everything rebounds. The collapsing material slams into the dense core and explodes outward in a colossal blast. This explosion is called a supernova. For a brief time, the star becomes brighter than an entire galaxy. Light floods into space. Shock waves race outward. Heavy elements are scattered across the cosmos, the very atoms that will one day form planets, oceans, and living creatures. But the story does not end with the explosion. Because deep at the center of this shattered star, the collapsed core remains. If the original star was only moderately massive, the crushed core becomes something called a neutron star, an incredibly dense sphere where matter is packed so tightly that a spoonful would weigh as much as a mountain. But if the star was massive enough, gravity continues its collapse. No known force can stop it. The core shrinks smaller and smaller. Gravity compresses matter beyond the limits of neutron stars. Space itself begins to curve more and more sharply inward. Eventually, the collapse passes a point of no return. The matter falls inward beyond a boundary where escape becomes impossible. And at that moment, a black hole is born. There is no flash marking this transformation. No dramatic signal announcing it to the universe. Just a quiet shift in gravity. A region of space where the pull becomes so strong that nothing, not gas, not dust, not even light, can climb back out. The newborn black hole sits silently where the star once burned. Where light once shined, darkness now remains. But this darkness is not empty. It is the result of gravity compressing matter to unimaginable extremes, bending space so deeply that it forms the mysterious object you are now approaching. As you drift through the quiet cosmos toward it, you begin to understand something profound. Black holes are not cosmic monsters appearing out of nowhere. They are the final chapter in the life of massive stars. A transformation from brilliance to shadow. From blazing light to perfect darkness. And yet, the story of this darkness is only beginning. Because as you move closer to the black hole itself, gravity begins to behave in ways even stranger than the collapse that created it. Space itself starts to curve more dramatically. Paths bend. Light warps. And somewhere ahead, hidden in the quiet darkness, lies a boundary beyond which escape becomes impossible. A place where gravity tightens its grip so completely that the universe itself seems to fold inward. And as you drift gently forward through the silent sea of stars, you begin to feel that invisible slope of space growing steeper, drawing you closer to the place where gravity allows no escape. You continue drifting quietly through the deep stillness of space. Behind you, the distant stars glow softly, their ancient light spreading gently across the cosmic dark. Ahead of you, the black hole waits silent, invisible, yet unmistakably present in the way it shapes everything around it. You are closer now. Still safe, still calm, but something about this region of space feels subtly different. Gravity is stronger here. Not in a violent or chaotic way, but in a quiet, steady pull that grows deeper the closer you move. It feels less like a force grabbing you, and more like a slope gently guiding your path downward. Imagine walking across a wide, open field. At first, the ground is flat and easy. You can move in any direction with equal effort. But slowly, the land begins to tilt. The slope becomes noticeable, and your steps naturally begin to drift downward. This is what gravity near a black hole feels like. You are not falling suddenly. You are simply moving along the natural curves of space itself. Long ago, scientists believed gravity was a mysterious invisible force pulling objects together. But in the early 20th century, a physicist named Albert Einstein offered a deeper way to understand it. He suggested that gravity is not a force in the usual sense. Instead, gravity is the shape of space. To picture this idea, imagine once again that space is like a soft, flexible fabric stretching across the universe. When nothing rests on this fabric, it remains smooth and flat. But when something heavy appears, a planet, a star, or an entire galaxy, the fabric dips beneath its weight. Nearby objects then move along the curved surface of that dip. They are not being pulled by an invisible rope. They are simply following the natural shape of space. Around Earth, this dip is gentle. A spacecraft can easily escape if it moves fast enough. Around a star like the Sun, the dip is deeper. Escape requires far more energy. But around a black hole, the dip becomes something far more dramatic. Here, the fabric of space does not simply bend. It plunges. Imagine a deep funnel carved into that invisible cosmic fabric, a well so steep that everything near it begins sliding inward. Light, gas, dust, even entire stars can be drawn toward this deep gravitational valley. And once something slides too far down the slope, climbing back up becomes impossible. You continue drifting toward that deep well. The stars behind the black hole appear stranger now. Their light bends more noticeably as it passes near the dark object ahead of you. Some stars appear slightly stretched, others duplicated in faint arcs of light. This strange visual distortion happens because light itself must follow the curves of space. When space bends, light bends with it. Astronomers call this phenomenon gravitational lensing. It allows black holes and other massive objects to act like cosmic magnifying glasses, warping and bending the light of distant galaxies. From your quiet vantage point, you can almost see these gentle distortions rippling through the star field. Space here is not flat. It is curved. Deeply curved. And as you move closer, you begin to understand that something important lies ahead. Somewhere in front of you exists a boundary. Not a wall. Not a surface. But a limit. A place where the slope of space becomes so steep that even light cannot climb back upward. To escape any gravitational field, an object must travel at a certain speed known as escape velocity. On Earth, that speed is about 11 kilometers per second fast, but achievable for rockets. Near the Sun, the escape velocity becomes far higher. But near a black hole, the escape velocity becomes extraordinary. At a certain distance from the center of the black hole, the escape velocity reaches the ultimate cosmic speed limit, the speed of light. Nothing in the universe can move faster than light. So when the escape velocity equals the speed of light, something remarkable happens. Escape becomes impossible. Even a beam of light, the fastest thing in existence, cannot climb out of that gravitational well. That distance marks a boundary in space. A horizon. Astronomers call it the event horizon. From the outside, it appears quiet and invisible. If you were drifting nearby, you would see no glowing line marking its edge. You would not feel a sudden shock or barrier. But crossing it would change everything. Because once something passes inside the event horizon, every possible path through space leads deeper toward the black hole's center. It is like drifting over the edge of a waterfall. Far upstream, the river flows gently. A boat can easily turn around and paddle away. But closer to the waterfall, the current grows stronger. At a certain point, the water begins rushing too fast to escape. Even if the boat turns and rows with all its strength, the current still carries it forward. Eventually, the boat reaches a line where escape becomes impossible. Beyond that point, the river flows only one direction: downward. The event horizon is like that invisible line in the cosmic river. From far away, it seems harmless. But once crossed, all paths through space lead inward. You float quietly in this region where the pull of gravity grows stronger with every gentle moment. Still, the universe remains calm. The stars continue shining. The darkness of the black hole reveals itself only through the subtle bending of light and the quiet slope of space beneath you. You realize something fascinating here. A black hole does not pull things in like a vacuum cleaner. It simply reshapes the landscape of space so dramatically that every path begins leading inward. Objects fall not because they are dragged. They fall because there is nowhere else for them to go. Gravity has folded space into a deep valley, and everything nearby naturally moves along its slopes. You drift a little closer. The event horizon lies somewhere ahead now. Still unseen. Still silent. Yet profoundly important. Because that invisible boundary marks one of the strangest limits in all of physics, the place where the universe hides its deepest secrets. Beyond it, light cannot escape. Signals cannot return. Information itself may vanish from the outside universe forever. And yet, crossing the event horizon might feel surprisingly ordinary. No sudden shock. No dramatic explosion. Just a quiet step across an invisible threshold. You pause for a moment in the calm darkness, surrounded by gently bending starlight. The black hole waits ahead. And somewhere just beyond your current path lies the mysterious boundary, the silent edge where escape ends and the unknown truly begins. In the next quiet moment of your journey, you may drift close enough to see what happens at that strange and invisible border. The place where the universe itself seems to whisper, "This far, and no farther." You drift closer still. The universe around you remains quiet and vast, but something subtle has changed. The gentle slopes of gravity you have been following now feel steeper, as if space itself is tilting more sharply beneath your path. Ahead of you lies a boundary unlike any other in the universe. The event horizon. It does not glow. It does not shimmer. There are no warning lights, no cosmic fences marking its edge. From where you float now, it looks like nothing at all, just another region of empty space. And yet it is one of the most profound borders known to physics. You hover near it, almost as if pausing on the edge of an unseen cliff. But this is not a cliff of rock or ice. It is a cliff in the structure of reality itself. The event horizon is the point where gravity becomes so powerful that the escape velocity equals the speed of light. As you learned before, nothing in the universe can move faster than light. That speed limit is woven into the very laws of nature. So once you cross this invisible boundary, even light itself cannot climb back out. Imagine throwing a ball upward from the surface of a planet. If you throw it slowly, gravity pulls it back down. If you throw it faster, it rises higher before falling again. But if you throw it fast enough, faster than the escape velocity, it will leave the planet forever. Now imagine a place where the escape velocity is faster than anything possible. No matter how hard you throw the ball, it cannot escape. Even if the ball were made of light, traveling at the fastest speed allowed by the universe, gravity would still pull it back. That is what happens inside the event horizon. From the outside, nothing strange seems to happen at the exact moment of crossing. There is no barrier waiting there. Space remains smooth and continuous. If you were drifting gently toward it, as you are now, you might not even notice the exact instant when you pass the boundary. And that is one of the most fascinating things about black holes. From your perspective, the crossing might feel perfectly ordinary. But from the perspective of someone watching from far away, something very strange would appear to happen. Imagine a distant observer watching your journey through a powerful telescope. As you approach the event horizon, your motion would appear to slow down. Slower. And slower still. Your clock would appear to tick more slowly compared to theirs. Your movements would stretch out across longer and longer moments. This effect is called gravitational time dilation. Gravity does not only bend space, it bends time as well. Near massive objects, time flows more slowly compared to regions far away from gravity's pull. And black holes create the most extreme examples of this effect anywhere in the universe. To the distant observer, you would appear to slow almost to a stop as you approach the event horizon. Your image would gradually fade and redden as the light you emit loses energy climbing away from the black hole's gravity. Eventually, you would appear frozen just above the horizon, fading slowly into darkness. But that is only what the distant observer sees. From your own perspective, time feels completely normal. Your thoughts move at their usual pace. Your experience of the universe remains calm and steady. And in a quiet moment, without drama or fanfare, you cross the event horizon. Nothing flashes. Nothing explodes. There is no sudden shockwave. You simply continue drifting forward, carried along by the natural curves of space. Behind you, the outside universe still exists. Stars still shine. Galaxies continue their slow rotations through the vast cosmic night. But something important has changed. No signal from where you are now can ever reach them again. The paths that light could once take outward now all bend inward instead. The geometry of space itself has changed direction. Inside the event horizon, every possible future path leads deeper toward the black hole's center. It is not like being trapped inside a cage. It is more like standing in a river whose current flows only one way. No matter which direction you try to swim, the water carries you downstream. Here, the river is space itself. And its current flows inward. You drift deeper into the quiet darkness. Surprisingly, the region just inside the event horizon may not feel dramatically different from the space just outside it, especially if the black hole is very large. The gravitational gradient at the horizon can be gentle enough that you notice little change at first. The universe behind you appears distorted now, its light bending strangely as it struggles to escape the immense gravity surrounding the black hole. Stars seem stretched into thin arcs. Entire sections of the sky may appear warped into glowing rings. Some light that tries to escape will curve around the black hole and return toward you again, showing distant regions of space in strange, repeated patterns. It is as if the universe itself has become a hall of mirrors. And yet ahead of you lies only darkness. Because the deeper regions of the black hole hide something far stranger than the horizon you have crossed. The event horizon is not the true center of the mystery. It is merely the doorway. Farther inward, gravity grows even stronger. Space curves more steeply. The paths available to matter and light narrow further. At the very center lies something physics still struggles to describe. A place where density becomes unimaginable. Where the familiar rules of space and time may completely break down. Scientists call this hidden point the singularity. But the singularity is still far ahead. For now, you continue drifting deeper inside the black hole's silent interior, carried gently along the invisible currents of space. Behind you, the event horizon marks the last place where escape was possible. Ahead of you, the mysteries of gravity grow stranger with every quiet moment. And somewhere along this inward path, another subtle change is waiting, one that will reveal just how deeply gravity can reshape not only space, but time itself. You continue drifting deeper into the quiet interior of the black hole. There is no wind here, no sound, no sensation of rushing movement. The universe remains strangely calm. The stars you once saw clearly are now distorted into faint arcs of light behind you, their glow bending along strange curved paths as gravity twists the geometry of space. Yet something even more subtle is happening now. Something almost impossible to feel. Time itself is changing. In your everyday experience, time seems simple and steady. Seconds pass one after another like gentle footsteps. Minutes turn quietly into hours, and hours into days. The flow of time feels constant, like a river that moves at the same speed everywhere. But the universe is not quite so simple. More than a century ago, Albert Einstein revealed something remarkable: time does not flow the same everywhere. It stretches and slows depending on gravity and motion. This idea belongs to a theory called general relativity, and black holes show its effects more clearly than any other place in the universe. Imagine time as another dimension woven together with space, like threads forming a single cosmic fabric. Scientists call this fabric spacetime. When gravity bends space, it bends time as well. And near a black hole, that bending becomes extreme. If you could watch two clocks, one floating safely far away in empty space, and another traveling with you here near the black hole, the two clocks would slowly fall out of sync. The distant clock would tick normally, but the clock near the black hole would tick more slowly. Not because the clock is broken, not because anything inside it has changed, but because time itself is flowing differently here. This phenomenon is known as gravitational time dilation. Gravity stretches time the same way it bends space. The stronger the gravity, the slower time moves. On Earth, this effect is extremely tiny. Time at sea level passes slightly more slowly than time high on a mountain because Earth's gravity is stronger closer to its surface. The difference is so small that you would never notice it without extremely precise atomic clocks. But near a black hole, the effect becomes profound. Imagine once again that distant observer watching you from far away. From their perspective, your journey toward the black hole appears slower and slower. Your movements stretch out like slow motion. Your signals arrive farther and farther apart. To them, your clock seems to tick more slowly with every passing moment. Eventually, as you approach the event horizon, your motion would appear to nearly stop entirely. But from your own perspective, time feels completely normal. Your thoughts flow at the same pace they always have. Your experience of moments passing remains steady and calm. This difference between perspectives is one of the most beautiful and puzzling consequences of relativity. Time is not universal. Each observer carries their own flow of time depending on where they are and how they move. You drift quietly onward, deeper into the black hole's interior. And now something remarkable begins to emerge from this strange bending of time. If someone far away could observe your journey long enough, they might see something astonishing. Suppose you remain near the edge of a black hole while years passed for the rest of the universe. When you eventually return to distant space, if that were possible, you might find that far more time had passed elsewhere than for you. Your experience of time would be shorter. It would be as though you had traveled slightly into the future. In fact, gravitational time dilation has already been measured on Earth with remarkable precision. Satellites orbiting our planet experience slightly weaker gravity than clocks on the surface. As a result, time passes a tiny bit faster for them. This difference must be carefully corrected for in technologies like GPS navigation. Without accounting for relativity, satellite clocks would drift and cause positioning errors within hours. But time moves only one way. You cannot travel into yesterday. You cannot step backward into the past. Time always carries you forward. Inside a black hole, gravity bends spacetime so dramatically that the direction leading toward the center becomes as inevitable as the forward movement of time. Just as you cannot stop time from passing, you cannot avoid moving deeper toward the center of the black hole. The path inward becomes part of your future. Every possible route leads there. It is not simply a place in space you are approaching. It becomes a moment in time waiting ahead of you. This idea can feel strange at first, that falling deeper into a black hole is as unavoidable as the next second arriving. But this is the extraordinary geometry created by extreme gravity. The deeper you drift, the more space and time twist together in ways that challenge the intuition we developed while living on planets under gentle gravity. Still, the journey remains calm. You continue drifting through the quiet interior of the black hole, carried forward along the smooth curves of space-time. But another effect of gravity is beginning to appear now. A difference in gravity from one part of your body to another. The side of you closer to the center of the black hole is pulled slightly more strongly than the side farther away. At first, the difference is tiny, barely noticeable. But as you continue deeper, that difference slowly grows. Gravity here does not pull evenly. It stretches. And in the strange environment of a black hole, this stretching becomes one of the most unusual experiences the universe can offer. Scientists have given this curious effect a playful name: spaghettification. And as you drift deeper toward the hidden heart of the black hole, gravity's quiet stretching begins to reveal just how powerful this cosmic force can truly become. You continue drifting deeper into the quiet interior of the black hole. There is still no sound here, no rushing wind or sudden turbulence. The universe remains calm and strangely peaceful, even though you are now in one of the most extreme environments that physics can describe. Yet gravity here is no longer perfectly uniform. Something subtle is beginning to happen. Gravity pulls more strongly on the parts of you that are closer to the center of the black hole than on the parts that are slightly farther away. At first, the difference is almost too small to notice. But it is there. Imagine standing on a hillside. Your feet rest slightly lower than your head, so gravity pulls a little more strongly on them. On Earth, the difference between those 2 points is so tiny that you never feel it. But near a black hole, the difference becomes much larger. Here, gravity changes dramatically over very short distances. This difference in gravitational pull has a special name in physics. It is called a tidal force. Tidal forces exist everywhere in the universe. Even the oceans of Earth feel them. The Moon's gravity pulls slightly more strongly on the near side of our planet than on the far side, gently stretching the oceans and creating the rising and falling tides. Most of the time, tidal forces are gentle and barely noticeable. But near a black hole, tidal forces grow incredibly strong. If you imagine your body floating vertically, with your feet slightly closer to the black hole than your head, gravity pulls your feet downward just a little more strongly than it pulls your head. At the same time, the sides of your body are pulled slightly inward toward the center. The result is a stretching effect. Downward pull at your feet. A slightly weaker pull at your head. And compression from the sides. Slowly, gently at first, this difference begins to stretch objects along the direction of gravity. Scientists, with a touch of humor, gave this process a memorable name: spaghettification. The name comes from the way objects would be stretched into long, thin shapes, resembling strands of spaghetti. It sounds playful, but the physics behind it is very real. Near smaller black holes, the tidal forces near the event horizon would be incredibly intense. Any object drifting too close could be stretched dramatically long before it crossed the horizon. But larger black holes behave a little differently. Supermassive black holes, like the enormous one at the center of our galaxy, have event horizons that are vastly larger. Because of this, the tidal forces at the horizon itself can be surprisingly gentle. An object might cross the horizon of a supermassive black hole without immediately experiencing extreme stretching. Only deeper inside would the tidal forces begin to grow truly powerful. This difference is one of the strange paradoxes of black holes. The larger the black hole becomes, the gentler its horizon can be. You continue drifting deeper along the invisible currents of spacetime. Gravity grows stronger. The stretching effect slowly increases. Imagine once more that you are floating along a cosmic river. Upstream, the water moves slowly and calmly. But as the river approaches a waterfall, the current begins to stretch and accelerate. The water at the front moves faster than the water behind it, pulling the river into longer, thinner streams. The same kind of stretching happens here, but with gravity shaping the flow instead of water. Space itself is guiding your path inward. And the deeper you move, the steeper that gravitational river becomes. Yet even here, inside one of the universe's most powerful gravitational wells, there is something quietly beautiful about the physics unfolding around you. Gravity is not acting with anger or violence. It simply follows its rules. Mass bends spacetime. Curved spacetime guides motion. And tidal forces emerge naturally from the changing shape of that curved landscape. Black holes are not monsters tearing matter apart with claws. They are places where the quiet mathematics of gravity becomes incredibly extreme. You drift farther inward. The universe outside the black hole has now faded almost completely from view. Light that once traveled easily between stars now struggles to escape the deep gravitational well surrounding you. Behind you, the distorted sky has dimmed into faint arcs of fading light. Ahead of you lies darkness. Not empty darkness, but a darkness filled with mystery. Because the stretching you feel here is only a symptom of something deeper. Something hidden at the very center of the black hole. Gravity continues to grow stronger as you approach that unseen point. The paths of space narrow. The curves of spacetime deepen. And somewhere far below you, at the deepest center of this gravitational well, lies the most mysterious feature of all. A place where matter is thought to collapse into an unimaginably small region. A place where density becomes so great that the known laws of physics begin to break down. Scientists call this mysterious point the singularity. But no telescope has ever seen it. No signal has ever returned from it. Even the equations of physics struggle to describe what truly happens there. As you continue drifting quietly inward, carried along by gravity's silent current, you realize that the stretching of spacetime around you is guiding everything toward that hidden heart. The singularity waits at the center of the black hole. And it may hold some of the deepest secrets about how the universe itself truly works. You continue drifting inward. There are no landmarks here, no stars to guide your path anymore. The outside universe has faded almost completely from view, its light trapped behind the event horizon you crossed long ago. What remains around you is darkness, deep and quiet. Yet this darkness is not empty. It is filled with gravity. Gravity that grows stronger with every gentle moment of your journey. The currents of spacetime are slowly guiding everything toward a single destination, the center of the black hole. A place scientists believe lies somewhere ahead, hidden beyond observation and perhaps beyond complete understanding. This place has a name. The singularity. The word sounds simple, almost ordinary, but it represents one of the deepest mysteries in all of physics. To understand why, it helps to imagine how matter behaves under gravity in the rest of the universe. When gravity compresses an object, it squeezes its material closer together. A cloud of gas can collapse into a star. A star can collapse into a dense neutron star when its fuel runs out and gravity overwhelms its internal pressure. In a neutron star, matter becomes incredibly compressed. Atoms no longer exist in their normal form. Electrons and protons are squeezed together to form neutrons, creating a sphere of matter so dense that a teaspoon of it would weigh billions of tons. For a long time, scientists thought this might be the ultimate limit of compression in nature. But black holes go further. When a massive star collapses beyond the limits that can support a neutron star, gravity continues squeezing the matter inward. There is no known force left to stop the collapse. Not atomic pressure. Not nuclear forces. Nothing. The matter keeps shrinking, compressed by gravity's relentless pull. According to the equations of general relativity, this collapse continues until the matter is squeezed into an extremely tiny region, possibly even a single point with almost no size at all. At that point, density becomes enormous. In fact, the equations predict that density would become infinite. This is what physicists call a singularity, a place where quantities like density and curvature grow without limit. But infinite density is not something the universe easily explains. Whenever infinities appear in physics equations, it usually signals that our current understanding has reached its limits. The singularity may not truly be a point of infinite density in reality. Instead, it may simply be the place where our current theories stop working. General relativity describes gravity incredibly well across the universe, from the motion of planets to the bending of light around galaxies. But it does not include the strange rules of quantum physics, which govern the smallest scales of nature. Inside a black hole, both gravity and quantum effects may become important at the same time. And our current theories do not yet fully combine those two ideas. Somewhere near the singularity, space and time themselves may behave in ways we have never observed before. You drift quietly through the darkness, moving closer to this mysterious center. If the predictions of relativity are correct, space itself continues narrowing as you approach the singularity. The curves of spacetime grow steeper and steeper. Every path through space leads toward that hidden point. In ordinary life, you can move freely in many directions. You can walk forward, step backward, turn left or right. But inside a black hole, the geometry of spacetime becomes so distorted that the direction toward the singularity becomes unavoidable. It is as inevitable as time moving forward. No matter which way you try to move, every possible path leads deeper inward. It is as though the singularity is not just a place in space ahead of you. It is a moment in your future. Eventually, every path through spacetime inside the black hole ends there. You continue drifting along that quiet path. Gravity stretches and curves the environment around you. The tidal forces you felt earlier continue shaping the geometry of space. Yet even as gravity grows stronger, the deeper mystery lies not in the force itself, but in the nature of the singularity waiting ahead. What truly exists there? Physicists have proposed many ideas. Some theories suggest that the singularity may not actually be a point, but rather a region where spacetime becomes incredibly curved and chaotic. Others imagine that quantum effects might prevent matter from collapsing into an infinitely small point. There are even ideas suggesting that black holes could connect to other regions of the universe through strange tunnels in spacetime called wormholes. But these ideas remain speculative. So far, no experiment or observation has been able to reveal what truly happens at the center of a black hole. The event horizon hides everything within it from the outside universe. Even light cannot carry information back from that deep interior. For scientists studying black holes, this creates a fascinating challenge. Black holes may contain answers to some of the biggest questions in physics about gravity, quantum mechanics, and the nature of spacetime itself. Yet their most important features remain hidden behind a cosmic veil. You continue your quiet inward drift. The singularity lies somewhere ahead, unseen and perhaps unknowable. But strangely, even black holes may not last forever. For many years, scientists believed that once a black hole formed, it would remain unchanged for eternity, a permanent feature of the cosmic landscape. Yet modern physics suggests something surprising. Black holes may slowly lose energy over time. Very slowly. So slowly that the process takes longer than the current age of the universe. But according to quantum theory, black holes may not be perfectly black after all. They may emit tiny amounts of energy, a faint glow that slowly leaks away from the event horizon itself. Over immense stretches of time, this radiation could cause the black hole to shrink, to fade, perhaps even to disappear. This strange possibility was first proposed by a physicist named Stephen Hawking, and it suggests that even the darkest objects in the universe are not completely silent. Somewhere near the edge of the black hole, quantum physics may allow energy to escape. A faint whisper of light from the darkest place in existence. And as you drift quietly through the deep interior of this mysterious object, you begin to wonder about that faint glow, the subtle radiation that may slowly carry energy away from the black hole itself. A whisper of physics that connects gravity, quantum theory, and the fate of black holes across unimaginable stretches of time. You continue drifting through the quiet darkness of the black hole's interior. Gravity surrounds you completely now, shaping every possible path through space and time. The singularity still lies somewhere ahead, hidden within the deepest curves of spacetime. Yet even while moving inward, another thought begins to unfold, one that changes how scientists think about black holes entirely. For a long time, physicists believed that black holes were permanent. Once formed, they would simply remain forever. Matter could fall inward. Light could disappear beyond the event horizon. But nothing could ever escape. Black holes were thought to be the ultimate cosmic prisons, objects that only swallowed energy, never releasing it again. But in the 1970s, a new idea began to emerge. It came from a physicist named Stephen Hawking, who explored what happens when the strange laws of quantum physics are combined with the powerful gravity of black holes. Quantum physics describes nature at the smallest possible scales, the realm of atoms, particles, and tiny fluctuations of energy that constantly appear and disappear in empty space. And according to quantum theory, even the emptiest regions of space are not truly empty. Space itself quietly shimmers with tiny fluctuations. Pairs of particles can appear briefly from the energy of the vacuum, exist for an incredibly short moment, and then vanish again. These pairs are called virtual particles. They are not stable matter like atoms or stars. Instead, they are temporary flickers of energy allowed by the uncertainty principles of quantum mechanics. Normally, these particles appear and disappear so quickly that they leave no lasting effect. But near a black hole's event horizon, something unusual can happen. Imagine a pair of these virtual particles appearing very close to the event horizon. One particle appears just inside the boundary. The other appears just outside. If nothing interferes, the pair would normally annihilate each other and vanish again almost instantly. But the event horizon changes the situation. If one particle falls inside the black hole while the other escapes outward into space, the pair cannot reunite and disappear together. One particle is trapped. The other is free. And the particle that escapes becomes real. It travels away from the black hole as a tiny amount of energy. This escaping energy is known as Hawking radiation. It is incredibly faint, far too weak to detect from the black holes we currently observe in space. But according to the mathematics of quantum physics, this process should happen continuously around the event horizon. A slow whisper of energy leaking away. At first glance, this might not seem very important. But it has a remarkable consequence. Energy cannot simply appear from nowhere. If a particle escapes the black hole carrying energy away, that energy must come from somewhere. And in this case, it comes from the black hole itself. Each tiny burst of Hawking radiation reduces the black hole's total energy slightly. Over time, that energy loss causes the black hole to shrink. Very slowly. Almost unimaginably slowly. For black holes with the mass of stars, the process takes far longer than the current age of the universe. A black hole with the mass of our Sun would take about 10 to the 67 years to evaporate completely. That number is so enormous that it stretches far beyond any ordinary sense of time. Even the stars in the universe will burn out long before such a black hole fades away. Yet according to physics, the process continues steadily. A faint trickle of radiation. Tiny particles escaping one by one, gradually carrying energy away. Over unimaginable stretches of cosmic time, the black hole would slowly become smaller. And as it shrinks, something curious happens. The smaller the black hole becomes, the faster the radiation process occurs. It begins to lose energy more rapidly. Eventually, near the very end of its life, the black hole could evaporate quite quickly, releasing a final burst of energy before disappearing entirely. What remains afterward is still uncertain. Some theories suggest that nothing remains at all. Others propose that tiny remnants of the black hole might survive. The truth is still unknown. But Hawking's discovery changed something profound about our understanding of black holes. They are not completely silent. They are not perfectly eternal. Even the darkest objects in the universe may slowly fade away. As you drift quietly through the interior of this black hole, the idea of evaporation might feel strange. After all, you are surrounded by gravity pulling everything inward. Yet at the edge of the event horizon, quantum physics quietly allows energy to slip away. A faint glow from the darkest places. And this connection between gravity and quantum physics is one of the greatest puzzles in modern science. Black holes bring together two of the most powerful theories humans have discovered: general relativity and quantum mechanics. Yet those two theories do not fully agree with one another. General relativity describes the smooth curves of spacetime created by gravity. Quantum physics describes the restless, fluctuating behavior of particles and energy at tiny scales. Inside black holes, both of these ideas must be true at once. And yet scientists are still searching for a deeper theory that can unite them. Some believe the answer may lie hidden in black holes themselves. Perhaps understanding their behavior will reveal the deeper structure of reality. But black holes do not exist only as isolated objects floating alone in space. Far beyond this one, enormous black holes sit quietly at the centers of galaxies, including the galaxy you once called home. These cosmic giants shape the motion of stars, influence the growth of galaxies, and anchor vast systems of matter across the universe. And as you continue drifting through the quiet darkness, your thoughts begin to expand outward again beyond this single black hole. toward the immense black holes that rule the hearts of galaxies. You drift slowly outward now, leading the intense pull of the black hole you just explored. The currents of spacetime carry you gently, like a leaf floating on a river that twists and bends in unseen ways. Though the singularity and the event horizon lie behind you, your mind remains focused on the mysteries you've just glimpsed. Yet ahead, the universe offers another marvel, one that exists not in isolation, but as a quiet architect of cosmic structures. Far across the vast darkness, entire galaxies stretch like shimmering islands in the cosmic ocean. Spiral arms curl gracefully, dotted with countless stars, clusters, and clouds of glowing gas. And at the heart of nearly every one of these galaxies, scientists believe, resides a black hole of extraordinary scale. These are not the modest stellar black holes formed from single stars. These are supermassive giants, black holes that weigh millions, sometimes billions of times more than the Sun. Imagine one such black hole quietly anchoring a galaxy. Its mass is so enormous that its gravity shapes the motions of stars hundreds of thousands of light years away. Stars orbit around it in regular, almost serene paths, their speeds and directions guided by the silent pull of this invisible center. You can picture an entire galaxy rotating slowly, its graceful arms tracing the paths of countless stars, all while the supermassive black hole remains at the core, silent, unseen, yet profoundly influential. Our own galaxy, the Milky Way, hosts one of these giants. Astronomers call it Sagittarius A*, a black hole about 4 million times the mass of the Sun. It remains invisible to the eye, but its presence is unmistakable through the motion of nearby stars, which orbit in rapid, intricate patterns, tracing out the invisible gravitational curves that surround it. This central black hole acts as the heart of the galaxy, holding the stellar population together, guiding orbits, and perhaps even influencing the evolution of gas clouds and star formation over billions of years. These supermassive black holes are mysterious in many ways. How did they grow to such enormous sizes? Did they begin as massive stars, collapsing into stellar black holes that then accreted vast amounts of matter over time? Or did they form directly from huge clouds of gas in the early universe, collapsing under their own gravity to create an already massive core? The answers remain elusive, but scientists continue to explore them through careful observation and sophisticated simulations. As you drift among the stars of these galaxies, you notice a fascinating connection between the black hole at the center and the galaxy surrounding it. The mass of the central black hole seems to correlate with the size and structure of its galaxy. Larger black holes tend to sit at the centers of larger galaxies, suggesting a deep link between these silent giants and the cosmic structures they inhabit. It is as though the black hole quietly guides the dance of billions of stars, shaping the galaxy's form and evolution in ways that are still only partially understood. Even beyond the gravitational pull, black holes affect their surroundings in more subtle ways. Gas spirals inward toward the central black hole, forming disks of glowing material called accretion disks. As matter falls inward, it heats up tremendously, emitting light and radiation across the electromagnetic spectrum. Some of this energy is channeled into powerful jets that shoot outward, sometimes spanning thousands of light years, carrying energy and matter back into the galaxy. In this way, black holes act as regulators, influencing star formation, galactic growth, and the movement of cosmic material. And yet, despite their enormous mass and influence, supermassive black holes remain quiet most of the time. Sagittarius A*, for instance, is relatively inactive compared to the brightest quasars observed in distant galaxies. It emits only occasional bursts of energy, leaving most of the time in a state of serene, almost meditative silence. This quietness allows the galaxy around it to maintain a graceful, stable structure, a cosmic dance choreographed by invisible gravity. You drift slowly through this vast region, letting your mind wander among the millions of stars in orbit around their hidden center. Time itself seems to move differently here. The gentle pull of the supermassive black hole affects space on such a grand scale that entire systems follow curved paths in a slow, predictable rhythm. The galaxy rotates, the stars trace their orbits, and yet the vast black hole at the center remains imperceptible, a hidden architect of the cosmic design. Even when a black hole seems still, it can harbor dynamic events. Occasionally, a star wanders too close, and tidal forces stretch it apart, scattering its material across the galactic core. Some of this material falls inward, feeding the black hole and adding to its mass, while some may be flung outward, enriching the surrounding regions with energy and elements. These rare but dramatic interactions reveal that even quiet giants are never entirely static, they are part of a living, evolving universe. And far beyond a single galaxy, black holes continue to shape the larger cosmic web. Clusters of galaxies, massive filaments of dark matter, and intergalactic gas clouds all respond to gravity on enormous scales. Supermassive black holes, in their own quiet ways, contribute to the structure and evolution of the universe, guiding matter, energy, and perhaps even influencing the flow of time in subtle, unimaginable ways. As you observe these distant galactic hearts, you begin to understand that black holes are not merely cosmic curiosities. They are central to the story of the universe itself. They anchor galaxies, regulate cosmic matter, and link the small scales of quantum physics to the vast scales of gravitational motion. They are both mystery and foundation, quiet yet powerful, hidden yet essential. You drift among the spiraling arms of the galaxy, sensing the harmony between motion and mass, between gravity and space, between the unseen and the luminous. The supermassive black hole at the core is a reminder that even in apparent emptiness, there can be a profound influence shaping everything around it. Stars, gas clouds, dust, and light all follow the gentle curvature of spacetime, directed in part by a hidden heart you cannot see but can feel through its effects. And as you float in this quiet, cosmic sea, a subtle thought begins to emerge. The supermassive black holes at the centers of galaxies may themselves be the seeds of further mysteries. What happens when two such giants meet? How do they influence the growth of the universe over billions of years? And could the collisions of these silent titans produce ripples in space-time itself, vibrations that we might one day detect across the cosmos? For now, you remain a quiet observer, drifting among the stars, aware of the immense, unseen forces at play. The supermassive black hole anchors the galaxy around you, holding billions of stars in a slow, graceful orbit. And yet it remains invisible, silent, and enigmatic, a hidden giant, patiently shaping the universe over unimaginable stretches of time. The deeper you drift in thought, the more you realize that black holes are not just singular points of darkness. They are keys to understanding how the universe organizes itself, how matter moves, and how cosmic structures endure. In their quiet, invisible presence, they teach that even in darkness, there can be form, purpose, and beauty. And somewhere beyond the stars, far beyond even this galaxy, another layer of the story waits, a story of black holes interacting, colliding, and sending ripples through the very fabric of space-time. The universe has much more to whisper, and the next quiet chapter of your journey will reveal how these colossal objects communicate through subtle vibrations that travel across the cosmos. You drift outward now, beyond the solitary supermassive black hole at the center of a galaxy, into the vast reaches of intergalactic space. The stars thin, galaxies become more distant points of light, and the universe feels quieter here. Yet even in this quiet, the cosmos is not still. On immense scales, black holes sometimes encounter one another, initiating one of the most graceful and mysterious dances imaginable. Imagine two black holes, each massive, dense, and hidden from sight, approaching along curved paths through the cosmic web. Slowly, over millions of years, they draw closer together. At first, their gravity tugs faintly, almost imperceptibly, each one influencing the other in subtle ways. Stars nearby may adjust their orbits, gas clouds may shift gently, but the real drama is hidden. It is a choreography of spacetime itself. As the two black holes spiral toward each other, their motion begins to accelerate. The gravitational pull strengthens, causing them to orbit faster and faster. You can imagine their paths like two dancers circling closer and closer together, moving in a rhythm dictated by the very curvature of the universe. Their steps are invisible, yet every ripple of their motion bends space around them, stretching and compressing it in ways that light itself cannot fully reveal. This motion generates something extraordinary, ripples in spacetime known as gravitational waves. Picture the fabric of the universe as a vast, calm sheet of water. If you place two massive stones into it, the water ripples outward, carrying the disturbance across the surface. In a similar way, as the black holes orbit and eventually collide, spacetime itself vibrates, sending waves outward across the cosmos. Those instruments, known as interferometers, detect gravitational waves by measuring minuscule changes in length as the waves pass through Earth. When the first detection occurred in 2015, it confirmed a century-old prediction from Einstein's theory of general relativity. Suddenly, humanity could hear the universe in a new way, sensing cosmic events that had been invisible for all of history. You imagine standing near the two black holes as they spiral together. Time itself stretches and warps in their immediate vicinity. From your perspective, you would see their motions as a graceful dance, bending light, curving spacetime, and warping the surroundings. Every orbit sends faint waves outward, vibrations of spacetime traveling at the speed of light, carrying information about the mass, spin, and energy of the black holes. It is as if the universe itself is speaking through the gentle language of geometry. Finally, the black holes merge. The two invisible dancers coalesce into one, forming a larger, more massive black hole. In that instant, spacetime ripples most intensely, and the gravitational waves carry the energy of the collision across millions of light years. The merged black hole rings like a bell, settling into a stable state, while the ripples propagate outward, traveling silently across the vast emptiness. The universe is still calm afterward. Galaxies drift as they always have. Stars continue to orbit unseen centers. yet the faint vibrations continue their journey, passing through entire solar systems, unseen by all except the most sensitive detectors. They are echoes of a violent yet strangely graceful cosmic event, a conversation between massive objects that leaves a subtle mark on the fabric of reality. These gravitational waves carry extraordinary information. By listening to them, scientists can learn about the properties of black holes that would otherwise be completely hidden. They can measure mass, spin, and distance. They can understand collisions that occurred billions of years ago, long before the Earth even formed. In a sense, gravitational waves act as a cosmic messenger, allowing humanity to peer into events that were once entirely inaccessible. And the story does not end with just two black holes. Across the universe, countless pairs of black holes collide. Some events are near, others billions of light-years away. Each collision sends ripples outward, overlapping and interweaving with one another across the cosmos. The universe is alive with quiet vibrations, a hidden symphony of gravity that continues whether or not anyone is listening. You drift quietly through this cosmic concert, sensing the interplay between mass, motion, and the geometry of spacetime. The black holes, once solitary giants, now interact in ways that create harmony and rhythm on a scale beyond human intuition. The quietude of the universe is punctuated by these subtle waves, invisible yet fundamental to the evolution of cosmic structures. Even as you float in silence, the implications of these waves unfold in your mind. Gravitational waves carry not only energy but history. They preserve the story of massive objects colliding, merging, and reshaping the universe. They remind you that the cosmos is not static, that even the darkest objects interact, dance, and communicate across unimaginable distances. And yet, despite their power, black holes remain silent to light, invisible in most ways. Only through the subtle language of spacetime vibrations can their interactions be sensed. Humanity has only just begun to listen. The instruments we build, the observations we make, and the patience to detect these tiny distortions are part of a growing awareness, a new way of understanding the universe that transcends the limits of vision alone. As you reflect on these cosmic collisions, a gentle thought arises: the universe has its own rhythms, independent of us, yet sometimes it reaches out, revealing its secrets through the quiet language of gravity. Each gravitational wave is a messenger, whispering stories of motion, mass, and transformation across the vast reaches of space and time. It is both awe-inspiring and humbling. You drift further, leaving the site of the collision behind, yet the waves continue to travel, unbroken, carrying the memory of the event across the cosmos. Somewhere, perhaps near a distant star, they pass unnoticed. Somewhere else, instruments on a tiny planet detect them, revealing their presence and offering insight into events billions of years old. In the gentle calm of space, you realize that listening to colliding black holes is more than just a scientific achievement. It is an invitation to experience the universe in a new way, to understand its movements not only by sight but by the subtle vibrations that pervade all of reality. Gravitational waves allow you, and humanity, to participate in a cosmic story that continues to unfold, silent yet eloquent. And as you drift quietly among the stars, contemplating the merging black holes and the waves they send outward, you sense that this is not the end of the story. There are still deeper mysteries ahead: the interplay of gravity, quantum physics, and the ultimate fate of black holes themselves. Somewhere further along, the universe waits to reveal its next secret, hidden in the silent, invisible currents of spacetime. You continue drifting through the quiet, expansive darkness beyond the regions where colliding black holes send their ripples across the universe. The stars and galaxies are distant now, mere points of light scattered across the cosmic sea. Yet in this vastness, the weight of curiosity presses gently against your mind. Black holes, once invisible curiosities, now stand before your thoughts as profound mysteries, objects that defy complete understanding. Even after centuries of study, after the discoveries of Einstein, Hawking, and countless others, black holes remain at the frontier of physics. They are a paradoxical combination, simple in description yet infinitely complex in detail. They are regions of space where gravity reigns supreme, yet they may also whisper secrets of quantum mechanics, a field governing the tiniest particles of reality. And somewhere in this tension between the immense and the infinitesimal lies a deeper truth, a truth that scientists are still trying to uncover. You reflect on what makes black holes so mysterious. On one hand, general relativity tells us that their gravitational pull is extreme, curving spacetime itself and drawing everything toward a singularity at the center. Time stretches, paths converge, and matter collapses beyond recognition. On the other hand, quantum physics describes a universe full of uncertainty, energy fluctuations, and probabilistic outcomes at the tiniest scales. These two theories, each powerful on its own, seem to clash when applied together inside black holes. Consider information, one of the central puzzles of modern physics. In our everyday life, information seems permanent. A letter you write, a memory stored in your mind, a digital file on a computer, all these preserve knowledge in some form. But what happens when information falls into a black hole? Does it vanish forever, swallowed by the singularity, or is it somehow preserved? Hawking's calculations suggested that black holes slowly radiate energy through Hawking radiation, yet the fate of the information that falls and remains unresolved. This is the famous information paradox, a question that continues to puzzle physicists today. The paradox is more than just a technical problem, it challenges the very foundations of how we understand reality. If information is truly lost, the deterministic structure of the universe, the idea that the present can predict the future, is called into question. But if information is preserved, as many physicists now suspect, then there must be mechanisms, hidden and subtle, by which black holes encode and release that information. Somehow, the universe keeps a record, even in the most extreme conditions. You drift slowly, imagining the interior of a black hole as a place where conventional notions of space and time dissolve. Perhaps the singularity is not simply a point but a boundary to our understanding. Perhaps inside, the universe operates under rules we cannot yet grasp. The very fabric of reality seems flexible here, a place where the enormous curvature of spacetime and the tiny quirks of quantum mechanics collide in a chaotic yet ordered way. Some physicists believe that black holes may ultimately point the way to a theory of quantum gravity, a unified description of the universe that reconciles relativity and quantum mechanics. Such a theory could explain how spacetime behaves under extreme conditions, how singularities function, and how the fundamental particles of nature interact with the geometry of the cosmos. Black holes, in this view, are not just strange objects, they are natural laboratories for the deepest laws of reality. You imagine drifting through the event horizon of a supermassive black hole, where tidal forces are surprisingly gentle at first. Inside, the singularity waits silently, the ultimate endpoint of gravity's inexorable pull. And yet, even in this extreme environment, quantum processes like Hawking radiation whisper of subtle energy escaping the black hole's grip. The universe, it seems, is never entirely hidden. Every action, every interaction, leaves some trace, however faint. Even the mathematics used to describe black holes becomes more mysterious the deeper you go. Equations predict infinities, points where density and curvature become extreme, and where conventional laws break down. Yet infinities often signal limitations of our models rather than physical reality itself. Perhaps the singularity is not truly a point of infinite density, but a region where new physics emerges, where spacetime and matter intertwine in ways beyond current understanding. Some theorists propose that black holes might even connect to other regions of the universe through structures like wormholes, though such ideas remain speculative. Others suggest that information swallowed by a black hole may be preserved on its event horizon, encoded in the geometry of spacetime itself, a holographic principle that hints at a deep connection between gravity, quantum mechanics, and the very nature of reality. The universe seems to be hiding its rules in these extreme, hidden places, waiting for careful observation and profound insight to reveal them. As you drift through this quiet void, the vastness of the cosmos mirrors the vastness of your curiosity. Each black hole, each ripple of spacetime, each flicker of quantum energy invites reflection. The universe does not rush, it unfolds patiently. And in the presence of such profound mysteries, you feel a sense of calm wonder, a quiet acceptance that some answers may remain just out of reach, but the pursuit of understanding is a journey in itself. Black holes also teach humility. They remind you that even with human intelligence, technology, and centuries of study, there are aspects of the universe that resist simple explanation. They stand as monuments to the limits of observation, to the subtlety of nature's laws, and to the interplay of forces far beyond ordinary experience. They are both terrifying and beautiful, their darkness containing the seeds of insight and imagination alike. Yet for all their mystery, black holes also connect to everything we know. They influence stars, galaxies, and the cosmic web. They generate gravitational waves that ripple across space, carrying messages from billions of years ago. They slowly radiate energy through quantum processes. They anchor cosmic structures and challenge fundamental principles, all at once. In their presence, you sense the deep interconnection of all things, from the tiniest particle to the largest cosmic structures. And so you drift quietly, reflecting on the paradoxes, the enigmas, and the subtle beauty of black holes. They are not just cosmic objects, they are keys to understanding the universe at its deepest level. Each discovery, each measurement, each detection of a gravitational wave brings you closer to grasping the hidden rules that govern reality. Yet the full truth remains elusive, a horizon always just beyond reach, inviting exploration and contemplation. In the stillness of space, you feel the gentle pull of curiosity, the same pull that drives physicists to study black holes, to imagine new theories, and to seek understanding where observation is limited. Black holes are more than mere objects, they are teachers, inviting you to consider the unity of the cosmos, the subtlety of its laws, and the profound mystery of existence itself. And as you drift in this quiet expanse, a thought arises softly: the universe holds secrets not just in its light, but in its darkness, and some of the deepest truths may wait silently inside these enigmatic, invisible giants, whispering their story to those who listen carefully. You drift slowly, gently, as if floating in a sea of indigo light. The universe stretches endlessly around you, stars twinkling softly in the distance, galaxies turning gracefully in their timeless orbits. Your mind feels weightless here, untethered, yet deeply aware of the vast tapestry of existence that surrounds you. The journey through black holes, through event horizons, singularities, and cosmic collisions, begins to settle into a quiet rhythm, like a song that slowly fades but lingers in your mind. The black holes you have visited, the singularities hidden beyond the reach of light, the colossal giants at the centers of galaxies, and the ripples they send across the fabric of spacetime, all these form a story of the universe that is at once mysterious and profoundly beautiful. They are reminders that even in darkness, there is structure, order, and a hidden logic that shapes everything. Gravity, time, and quantum mechanics converge to create a universe that is both predictable and astonishingly complex. As you drift in the soft cosmic quiet, you notice the gentle interplay between light and dark, presence and absence, known and unknown. The universe does not demand that you understand everything all at once. Instead, it invites you to witness, to feel, and to imagine. Each black hole, each ripple in spacetime, is a point of reflection, a reminder of the delicate balance between curiosity and calm, between exploration and rest. The immense darkness of black holes no longer feels threatening. Instead, it becomes a space of contemplation, a place where questions linger without urgency. You feel the pull of gravity less as a force of fear and more as a gentle reminder of the universe's intricate design. The singularities that once seemed so unknowable now feel like quiet symbols of limits, places where understanding bends and stretches, inviting humility and wonder in equal measure. Far off, galaxies drift in elegant silence, their supermassive black holes anchoring them as they move through the cosmic web. You sense the subtle influence these giants exert, their pull shaping the evolution of stars, gas clouds, and the structure of the universe itself. The universe is alive with invisible interactions, gentle forces weaving a delicate web of matter, energy, and space, yet the rhythm of these forces is calm, enduring, and timeless. As you rest here, your thoughts wander back to the more intimate mysteries, the way gravity bends time, how matter stretches under tidal forces, how even the darkest objects may radiate faint energy over unimaginable spans of time. You realize that these processes, though extreme, are part of the same universe that nurtures life, planets, and the quiet moments of reflection in your own mind. The cosmos is not separate from you, it is a continuum in which curiosity, understanding, and wonder are threads woven into the fabric of reality. Your awareness expands beyond black holes, beyond galaxies, beyond clusters of stars. You begin to feel the universe as a whole, a living, breathing expanse of space and time. Each gravitational wave, each particle of light, each rotation of a galaxy is part of a symphony that has been playing for billions of years. You are part of this symphony, even in your stillness, even as you drift toward the quiet edge of sleep. Time feels different here. The intense stretches of relativity near black holes, the slow fading of Hawking radiation, and the spiraling collisions of massive objects all blend into a timeless awareness. Minutes, hours, and eons coexist in your perception. The universe seems to fold upon itself gently, allowing you to experience its vastness without haste, to understand its complexity without pressure. You are a calm observer, floating in a cosmic lullaby that invites rest and contemplation. Even as your mind absorbs these profound insights, you notice that the universe keeps moving. Stars continue to shine, galaxies continue to rotate, and black holes continue their quiet work of shaping spacetime. The cosmos is not still, but neither is it frantic. Its motions are deliberate, harmonious, and often hidden from immediate sight. You feel the calm pulse of existence itself, a rhythm that has persisted long before you and will continue long after, carrying both mystery and clarity in equal measure. You reflect on the journey you have taken from the quiet approach to a single black hole, through the edges of event horizons, the stretching of spaghettification, the mysteries of singularities, the faint whispers of Hawking radiation, and the cosmic dance of colliding giants. Each chapter of this journey has unfolded with care, revealing the universe's hidden structures while maintaining a rhythm of quiet introspection. Science, imagination, and wonder have intertwined, creating a tapestry both gentle and profound. The knowledge you have gained is not a conclusion, but an invitation. It is a gentle nudge to continue pondering, to remain open to discovery, to accept that some answers may always lie beyond reach. Black holes, in their silent power, demonstrate that the universe is as much about what is hidden as what is visible, and that curiosity itself is a bridge between comprehension and mystery. In this quiet, reflective space, you allow yourself to rest. Your thoughts drift gently, unhurried, like starlight traveling across the immense distances of the cosmos. You feel a sense of closure without finality, an understanding that is deep yet open-ended. The universe has shared its stories, and yet it leaves room for dreams, for questions, for the quiet wonder that continues even when words and equations fall short. And now, as you drift further towards sleep, the edges of consciousness and cosmic awareness blur. The stars around you glow softly, like tiny beacons guiding the mind toward rest. Black holes, silent and mysterious, continue to shape space, time, and matter, carrying secrets that may one day be revealed, yet for now remain gently hidden. In this calm, the universe and your mind become a quiet, eternal rhythm, a story without end. Somewhere deep within that vast, dark expanse, the mysteries you have followed continue their eternal work, waiting patiently for another mind to listen, to reflect, to imagine. And in the gentle quiet that surrounds you now, curiosity fades softly into rest, leaving only calm, understanding, and the serene certainty that the universe continues its quiet story while you drift peacefully towards sleep.